Hello, this is section 1911. It's called multiple substituents. Now, when you have an aromatic ring with two substituents and you want to synthesize that, you need to think carefully about the directing effects of the different groups. And you want to begin the synthesis with the director of the substitution that you have. Let me give you an example. Now, here we have metachloronitrobenzene, and what we want to do is synthesize this. Now, of course, we start with benzene and we stick on one group and then we stick on the second group. But what you want to do is realize that these two groups right here are meta with respect to each other, okay? And this is a meta director. So what you want to do is start with benzene, okay, and create nitrobenzene. Now, since the nitro group is known to be a meta director, when we chlorinate this, it'll snap on right in the meta position. Let's look at another example. Now, when you look at this example, a methyl group is known to be an orthopara director, and a halogen is known to be an orthopara director. So here, in terms of the directing effects, there would be no right or wrong answer. You could start with benzene, and you could first install the methyl group, and since benzene is perfectly symmetrical, there would be only one choice here. We're going to put the methyl position to the bottom left. And then, since this is an orthopara director, we know that chlorination should occur at the ortho position and the para position. Granted, we only want the para isomer, but we just can't avoid the fact that some of the ortho isomer will form as well. So we'll just go ahead and write the product that we want. Okay, we know we're going to form that, and some of the ortho as well. Okay, so that's when you have just an ordinary di-substituted aromatic ring. It's very easy to plan the synthesis. Okay, now when you have two or more groups, you need to think carefully about where the third substituent is going to be introduced. Now, the first rule, okay, is that if two things direct to the same position, you go ahead and go there. There's no doubt, okay? The analogy I give is in the summer, if you're on the couch playing some video games and your father says go mow the lawn and your brother says go mow the lawn, there's no conflict of interest. They're both telling you to mow the lawn. So you're probably going to be directed to mow the lawn. So let's take an example. Let's look at an example of that. Okay, so I'm going to use colored pencils here to carefully identify the directing groups of each of these groups. So the hydroxyl group, this is a phenol, is an orthopara director, okay, and it's going to direct ortho where there are hydrogens And it also directs para, yes, I know, but there's not a hydrogen there at the para position. So I'm not going to box up that carbon because we can't put another substituent where the nitro group is, okay? So the hydroxyl group is directing to those two positions that I've highlighted with a yellow square, all right? Now let's look at the nitro group. We're going to use a circle here in a different color as well. The nitro group is known to be a meta-director. Okay, so with respect to the nitro group, 1, 2, 3 carbons over is the meta group. The nitro group is going to direct to the same carbons highlighted here with a white circle. So if you do this reaction with, I don't know, a chlorination, let's do a bromination, let's do something a little different than the last example. So if I treat this with iron tribromide catalyst and stoichiometric amounts of bromine, I'm going to get the product where I have the bromine group introduced ortho to the hydroxyl group and meta to the nitro group. Okay? There might be minor products, but that's predicted to be the major product. Okay? So if both directors direct, the reaction occurs on that carbon. Okay. Rule number 2 is the stronger director wins. So again, let's use that couch example. If you're on the couch playing a video game and your brother comes in and says, hey, come with me and let's go skateboarding out at the skateboard park, and your dad says, go mow the lawn. Your father is generally considered to be the stronger director, so you're probably going to go out and mow the lawn, okay? There is a conflict of interest there, but the stronger director is going to direct your actions, okay? So let's take a look at that now. Now here it's important to realize the table that I showed you in the previous video about strong directors, moderate directors, and weak directors, okay? Now, when you look at these two groups, they are both ortho-para directors. But when we look at the methoxy group, this is one of the strongest directing groups. So this is a strong ortho-para director. And it's going to direct to the two orthocarbons adjacent to this methoxy group, but not the paracarbon because there's no hydrogen at that carbon. There's a chlorine, okay? So we can't substitute chlorine. We can only substitute hydrogen. Now, this chlorine here is a very weak ortho-para director. It's a weak ortho-para director as well. Okay, so let's highlight the two carbons here with yellow. We're going to direct to those two orthocarbons. So you might think any one of these 4 positions is going to be substituted. But in fact, we use this rule that the stronger director wins out. So your methoxy group is going to be the stronger director. And if we treat this with, let's do a nitration, this example, nitric acid and sulfuric acid, H2SO4, we will get a nitro group introduced into the aromatic ring, and this nitro group will be preferred to be ortho to the methoxy, which is a stronger directing group. Okay. Now, yes, we would expect minor amounts of a nitro group being introduced ortho to the chlorine, but here we're just concerned with drawing the major product, okay? All right. So rule number 1 is that if both things direct, the substituent's going to go there. Rule number 2 is that the stronger director wins out. Those are basically the 2 major rules for figuring out where to put the substituent. So let's go ahead and look at some examples here. Best way to do that is to look at problem 1919. So in problem 1919, we're not really told what electrophilic aromatic substitution reaction they're doing, but we have these aromatic molecules that have 3 different substituents, okay? So we're going to use those 2 rules that we've talked about to determine what happens, okay? So we'll use colored pens here to identify what's going on here, okay? Nitro is a weak director. Nitro is a weak director. And maybe I should use different pencils here and slow down. So this nitro that I've circled with a green circle directs meta, but not that second circle that I did. I'll erase that because there's no hydrogen attached there, okay? Next, we have this magenta nitro group, and that's going to direct meta to that nitro. And then we have the methyl group. And this is an alkyl group. Remember the phrase no chops. Carbon is an ortho para director. Now there's no hydrogens ortho. There is a hydrogen para to the methyl group, so it's going to direct here. So this is a rare instance where all 3 directors are all directing to the same carbon. So that's going to be the position. Okay, so I'll put the answers in red here for this video. So the answer is going to be this carbon right here as a result of all 3. Okay, let's look at the next problem here, B. So here's our nitro group right here. The nitro is a weak director. Ortho meta is here, and the other meta is blocked. Okay, the other nitro group here shown in magenta directs meta, which is blocked here, but the other one is here. Okay. Oh, I'm sorry, that directs here, okay? So far, both of the nitro groups are directing to the position at the top of the ring. In yellow, this is also an ortho para director, okay? Now the para position is blocked by this. This ortho position is blocked by the nitro. So the only position that's ortho to that group is right here, okay? So again, we have all 3 substituents directing to the same position located right here in red, okay? Let's take a look at our next example. Here we have oxygen with a lone pair directly attached to the aromatic ring, and that is a moderate or a strong, depending on how you count it, ortho para director. Okay, that belongs to the no chops phrase. Oxygen with lone pairs is an ortho para director. So let's identify that's going to be right here only. This ortho position has no hydrogens, and this para position has no hydrogens. So we don't think about those. I'll erase those X's. Our other substituent here, we'll use green, is an ester, okay? And there's a pi bond right next to the aromatic ring, so that's an electron withdrawing group. All electron withdrawing groups are meta directors, okay? There's no hydrogen at this metacarbon, but there is a hydrogen at this metacarbon, okay? Finally, we'll analyze the methyl group here with the yellow box, and that's an ortho para director. So here's ortho, okay, and here's para. Okay, so now we kind of have a conflict of interest. A lot of different things are saying what, okay? So remember again that this is a strong electron donating group. It's a strong director, and the stronger director is going to win, okay? So this is the strongest director that I'm pointing an arrow to. The methyl group is a moderate or a weak director. And so we're going to position ortho to that. So let's go ahead and highlight that. Okay. The stronger director works. Okay. Stronger directors are strong activating groups. They're ortho para directors. Let's look at this next example here. Let's use yellow for this methyl group. This methyl group is an ortho para director. Let's use green for this methyl group. This guy here is an ortho-para director. Okay, so those are two director groups, and they're both directing at the same location. And then we have a cyano group. A cyano group, remember, is a carbon-nitrogen triple bond. That's your pi bond, which is considered to be an electron withdrawing group. So that's going to be a meta director. Okay, and those two are metacarbons. Now, because of the symmetry here in this molecule, you can only form one product. So I'm just going to pick the carbon on the left. Okay. If you draw the product on the right and you flip it like a pancake, it'll be the same molecule. Okay, so it's not different. Let's continue looking at these. Here we have a nitrogen with a lone pair of electrons. So that's going to be your best, strongest director, and that's an ortho-para director. So here's the ortho carbon, here's the para carbon. Your methyl group is going to be considered a weak director, and that's going to be ortho-para. The ortho carbons have no hydrogen, so it's going to be here. Okay, so that's weak. And then here in green, we have the pi bond, which makes this an electron withdrawing group. Okay, which makes that a very poor activator of an aromatic ring. If we draw the metacarbons, there's no hydrogen here, there is a hydrogen here. Okay, so we have a conflicting directions here. Somebody's saying do this, somebody else is saying do this, the other person's saying doing this. Who's right? Well, remember that the strongest director is going to win. So in yellow, this is what we want to consider. We're going to form two possible products, one in which reaction occurs at this carbon and one in which reaction happens at that carbon. Okay? Now I know two of the groups are saying go here, but they're very weak directors. Okay? The nitrogen with a lone pair is the strongest director. It has the loudest voice in terms of where this reaction is going to occur. In F, we have 4 different groups. They're all ortho-para directors. So let's take a look. This bromine is an ortho-para director. That's the only available carbon that's ortho or para to the bromine that has a hydrogen atom. This one here is a methyl group, and it directs to the para carbon as well as to the ortho, but the orthos don't have any hydrogens. In kind of light blue there, it's an ortho-para director. This is the only one here that's available. And then we have the hydroxyl group. A hydroxyl group is the strongest director. It's going to trump all of these other ones, and it's going to direct ortho and para, so it wins out. That's where you're going to have reaction. Okay? So that's a nice little summary of the rules 1 and 2. Now a third rule that you have is, generally speaking, like tic-tac-toe, you have no 3 in a row. Okay. What do I mean by that? Let me give you an example. Let's say we have 1,3-dimethoxybenzene. Okay, and let's analyze what happens if we try to brominate this. Okay, now the idea here is that this methoxy group is a very strong activator. It's an ortho-para director. It's going to direct to these 3 carbons, the 2 ortho carbons that have hydrogens and the para carbon that has a hydrogen. In light blue, we have another methoxy group, and that guy there circled in blue is going to direct to, hey, that's convenient, to the same exact locations, okay? But these 2 positions, there's 2 possible positions on the plane of symmetry, okay? This molecule has a plane of symmetry running right down the middle. At the top carbon, that's one product, and then the second product would be if we react those 2 points or carbons off the plane of symmetry. Now, this carbon right here, yes, it does have a hydrogen that can be replaced, but it's sterically hindered by these large methoxy groups. So you're not going to have a reaction here. And an easy way to remember that is that would form a product that would have 3 substituents in a row. Now, sometimes you can't avoid it, and it's going to happen. But when there's a choice, like there is with this one, we're gonna call this minor. We're not going to say not formed. I realize everything's going to be formed in some amounts. But so what you're not going to form is that, because you have 3 substituents in a row. What you're going to form is this molecule here. And you can pick the left carbon or the right carbon to place your bromine on. Okay? That's predicted to be the major product because there's only 2 substituents in a row. So that's not as much steric hindrance. Okay? So that in its entirety is the 3 rules. The Klein's textbook discuss steric effects. Okay? Steric effects. And this can be used to explain the major and minor when you're predicted to get both things. So for example, if you have this molecule here and you want to do a nitration reaction, we know that the tert-butyl group is an alkyl group, and that's an ortho-para director. And so normally we would draw both of the products as possibilities, okay? We would draw a nitro group here, that's ortho, and we would draw a nitro group that's para to the starting tert-butyl group. Now, the tert-butyl group is rather large, and so you would expect maybe there to be some steric interactions during the transition state, and the rate for formation of this to be rather slower. So the textbook would like you to remember that that's minor and this is major, but realize you're going to form both. Whether it's 80-20 or 70-30 or 60-40 mixture, I don't know. Depends a lot on the reaction conditions and temperature and solvent, things like that. Okay? So when you have something like this, and the book gives this exact one here as an example. I'll do a nitration again. We have 2 groups. Here's an isopropyl group that directs at the ortho positions. The para is blocked. And here's a methyl group that directs to the 2 ortho positions. The para is blocked. So you might anticipate drawing 2 products. Okay, so let's go ahead and draw the 2 products that we would get here. The analogy here would be you have 2 brothers. One says, let's go ride bikes. Another one says, let's go fishing. You're like, okay, I kind of get to choose, right? Now the nitro group could go ortho to the isopropyl group, or nitro could be ortho to the methyl group. This is going to be the major product because a methyl group is smaller and has less steric interactions between the nitro. Okay, this is a larger group, and so it's going to have greater steric interactions between the nitro group. So this is going to have more steric strain. It would be predicted to be minor. This one over here has less steric strain. It's going to be major. Okay? So with that analogy of going out with your brother to recreation in some fashion, you're going to pick the brother that maybe you're not in a fight with, right? Less strain with. Anyways, my analogies don't always work out, but that's the chemistry, okay? In problem 1922, now we need to really think carefully about things. So let's do problem 1922. Okay, in problem 1922, it looks just like the problem 1919, but let's just go ahead and analyze things and see what we come up with. I suspect we're going to have to apply rule number 3, which is sterics, okay? So here we have the strongest director. We know it's the strongest director because we have an oxygen right next to the aromatic ring with lone pairs, and that's an ortho para director. The para carbon is blocked by a methyl group. This carbon here is a methyl group. That also is an ortho para director. There's only one carbon that could possibly go to. Now, nitro is an electron withdrawing group. That's never going to be the strongest director, right? So compared to a phenol or an alkyl group. But I'll just go ahead and analyze wherever it goes anyway, just so we could refresh our memories. This nitro group normally directs meta. So that's going to be here, which is the only carbon available. Okay. Now we use rule number 2, I believe it is. The stronger director directs, and I'll use the color of purple that we analyzed that with. So the OH is a stronger director. Okay. And we want to use rule 3, no 3 in a row. Okay, we don't want to put it here because we have a nitro group on one side and a hydroxyl group on another, and reaction at that center is rather sterically hindered. So what we do want to do is react here. Okay, so I'll put all of the answers with a red dot in this video. Let's analyze further what's going on with part B. So here's a methoxy group. That's going to be the strongest director, and that's an ortho para director. Here's the 2 ortho carbons. The para carbon is blocked. Bromine is a very weak ortho para director, so it's going to direct here, and there's no other ortho or para carbons with hydrogens. And the nitro group, once again, is the weakest director, and that's going to be meta, and that's going to be here, which is the only one that has hydrogens meta to the nitro group. So we're going to use these exact same 2 rules again. The O-methoxy group is the stronger director, and we don't want to form 3 in a row. Okay, 3 in a row would be right there. So we don't want to do that. What we want to do is direct here. There's a little bit more steric room for the reaction to occur. So we're going to have reaction here. Okay. Let's continue the analysis. This is a tert-butyl group. This is an ortho para director. Okay. This is a tert-butyl group, and it's an equally good director, and it directs to the 2 ortho and the para. Remember, para to that circled one, ortho to that circled tert-butyl group. Okay, so all 2 substituents are directing to the same locations. We want to use rule 3 here, no 3 in a row. So we don't put a substituent there. We get reaction, and we put something there. Okay? So that's problem 1922 in the client's textbook. There's a part D and E. I'll let you work on those yourself. Okay? The textbook talks about blocking groups. That's something I skip in my course. If you're interested in that, you should look over how sulfonic acids can be used as a blocking group to introduce a block, and then there's a reaction, and then you can unblock it. Okay? And problem 1925 goes into the use of blocking groups. Okay? All right. So that's it for this chapter. Thanks for watching, and stay tuned for synthesis, which comes up next.